The following content has been provided by RWTH Aachen University.
The simplest way to do this is using grammars. And you guys probably remember grammars from your theoretical computer science classes or introductory computer science classes. So can somebody tell me what this Backus-Naur form, this BNF-like grammar here describes? What is this grammar telling us? Come on, you've all been through basic computer science training. I know it's been a while, but they told you it would come back, right, at some point. So, easy enough. Give it a shot. Yeah?
I don't know.
No idea what this does? Yeah?
There may be braces around atoms, and if you have a brace going open, then you have to close it.
Okay. So that's part of the story here. We're really looking at a recursive definition here, right? It's saying any expression can either be an empty expression or it can be an atom followed by an expression. So that means we can have atoms, 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 atoms. Or it can be an expression that is enclosed by parentheses plus another expression. So this basically describes a simple form of an expression that consists of atoms and brackets around atoms. Right? That's the idea behind this. So with this way, you can describe textual interfaces quite well. So here's an example of that. This is an extension by Schneiderman that basically takes the idea of a grammar described here and extends it a little, because now we have parts in the grammar that are delivered by the user and parts that are delivered by the system. Schneiderman calls this a multi-party grammar. Ben Schneiderman, by the way, also an author of a very successful, influential textbook. What is it called? Designing the User Interface, I think. Schneiderman, yeah, DTUI, I would believe. That's also a book that's definitely worth taking a look at. Anyway, so let's see if we can find out what this multi-party grammar here describes. Can anybody give me an idea? What happens when this grammar is basically being applied, executed? Yeah?
User has to type login and the name, and the computer responds with a hello and then in brackets the name.
Exactly. So that's what's going on here. Should be pretty clear how that's happening. The idea is we've now described an interface in a way that I could easily see, this formally, you can subject that to all kinds of formal verifications, whether it's complete or whether there's any kind of dead ends in it and stuff like this, whether it terminates, blah, blah, blah. Stuff that you couldn't do when you have a basic statement, right? So this description is already easier or better, more suited to a simple textual interface that I'm trying to provide. So this is great in general for command line user interfaces, like Unix commands, right? And you're typing on a command line, and you hit a couple keys, hit enter, system does something, and then it's your turn again. That's classic turn taking, very simple sequential flow of interaction between the user and the system, all described by a series of characters on the screen. Very simple, very easy to describe with this kind of language. But it also works for things like banking ATMs, right? If I have an ATM that just displays some simple text in a simple mask, and then asks you about pressing one key, and then you go back and it asks you some more text. That's also easy to describe with this. Doesn't work so well for graphical user interfaces. Why? Because the user moving a mouse around and pointing at things, yes, you could describe it when you abstract away from all the details of the mouse movement, but there's a fundamental problem when you start using a graphical user interface as opposed to a textual one, because the user could do a lot of different things at the same time. And we'll see a better way of describing that in a minute. For now, here's a couple more examples of grammar-like descriptions. You guys all have heard of regular expressions, of course. in which basically a star behind or an asterisk after a term means that it could be repeated 0 or more times. So look at this sequence here. What kind of application could use this sequence of interactions? And the names here give you a little bit of a hint to what kind of application that is. Got something to do with graphics. You've probably done this interaction many times. Yes?
If you want to draw a polygon,
Aha!
and then you select the tool, and then you click multiple times, and you double click to finish the last line.
Exactly. So this basically says I select a tool to draw a polyline or something like this, and then I need to click at least one time to position one point. Then I can, if I want to, click several more times to specify more points along the line, and I complete the line by double clicking. So what's interesting here is we've already guessed what this is, but you realize this is a very high level of abstraction, right? It doesn't tell us anything about the mouse movement going on in between these clicks. So there is no detailed interaction description, and there's also no semantics, really. I only know that this needs to happen once, this needs to happen once, this needs to happen 0 or more times, and this needs to happen once. But the names suggest what it does, but it could be something completely different, right? We haven't really specified what happens. The real semantics aren't behind it. Give you another example. The Unix copy command. Raise your hand if you've ever used the Unix command line. All right, good. I need to just do a reality check here each year that we're still good. This is what you get back when you ask about the help page for Unix. It starts with this. That's the synopsis of what the command looks like. And again, this basically specifies nicely what kind of options you can use, right? Tells you, OK, I need to type CP if I want to use the copy command. And then I can use -R, and then I can use -H, or -L, or -P. These three are exclusive to each other because they come with an OR sign here. And then comes the second block of commands, which are also mutually exclusive. Then comes the third optional command here. Then comes a source file and a target file. Or same thing, but source file and more source files. And then finally, a target directory. OK. Now, that's a nice specification. That's great. But what we see here is it's telling us that the various parts, like, for example, the recursion policies and the override policies are captured in these different things. It's short, it's precise, but it's not exactly easy to read. And it also requires additional information about semantics. What do I mean by that? I could write a command, a program, in a few minutes that works exactly like what's specified here, accepts all the right commands, but does nothing. Right? Because this synopsis only tells me the syntax of how I need to invoke the command and what kind of syntax it accepts. It doesn't tell me what the command actually does. So we're still lacking that part of the description. Now, when we get to graphical user interfaces, then production rules make a lot more sense. And again, that's probably something you've heard in your computer science lectures before. Whenever turn taking is not only sequential, when a lot of different things can happen concurrently, then production rules make a lot of sense. They are an unordered list of rules of the format of if condition, then some action. And the condition is always based on a current state or pending events. And the rules are always potentially active. So all the rules can fire as soon as their condition is fulfilled. Works great for concurrency, not so great for sequence. To give you an example, we can try to take this line drawing that we just had and turn it into a production rule system. That's kind of a weird use of it because the line drawing was a classic example of a sequence of actions. So the grammar for it made perfect sense. If we use a production rule, it will be a little difficult to do it in a production rule. But let's look at how this could work. We'd have a first token that's called select line. When that's available, that means that the user selected the select line command. Then we create a token that's called first. When there is a click action, a click event, and the first token is available, it was just generated with this thing above there, then the second rule can fire, and it will create a token called rest, which means we can now specify the rest of the polyline. If a rest token is available and the user clicks, then we generate another rest token. And finally, if the user double clicks and we have a rest token available, we basically move to the final state of this production rule system here, which is draw the line. So essentially, and this is put in parentheses saying like this is where the action actually happens, right? This is executed. Essentially, this means that this rule could fire immediately, but it's held back because it needs this rest token to be there. That's only generated when the first then this rule here has fired, and that only fires when it has a first token, and that only gets generated by this first production rule. So by inserting these additional tokens, we've kind of made all these parallel production rules here be able to fire at the in a particular sequence. But you can see that once a rest token is available, these two things will fire depending on what the user does, whether he single clicks or double clicks. So here we've modeled the parallel options that the user has in production rules. The basic idea is that we are here basically taking events and add them to a list of pending events. We have a little queue of events that are coming in. And first and rest are really just internally generated helper events or tokens, if you like. This is not very good at modeling state, because state needs to be modeled with these helper events here. The grammars are much better at preserving state, because there we automatically move from left to right. So in a way, you can remember if you have lots of stuff going on in sequence, like in a command line terminal, for example, then grammars are a good idea. If you have a lot of stuff going on in parallel, production rules are a better choice.
This content was provided by RWTH Aachen University.